So hello, I'm going to be telling you about the current observational status of primordial black holes. I'm going to start by talking about the history of primordial black holes, in particular trying to explain why there's been such a surge of interest in recent years. Then I'm going to talk about how they can form in the early universe, before next talking about observational constraints of their abundance and potential signatures of their existence. And finally, I'll talk very briefly about some open questions in the field. If you'd like to know more about this topic, I've highlighted some review papers here. The first one is by Bradley Kavanagh and myself. The second one by Bernard Carr, who is probably the world expert on primordial black holes, and also Florian Kuhnel. And then finally, this one by Bernard and his collaborators takes what they call a positive perspective. They're looking at potential evidence for primordial black holes rather than constraints on their abundance. So starting with the history, and here I'd like to highlight a textbook on primordial black holes that's going to come out in the next few months. And Bernard Carr and I wrote the opening chapter for this on the history, and that chapter is available from the archive if you'd like to look at it in more detail. So primordial black holes, the idea was first come up with by Zeldovich and Novikov and then Hawking in the late 1960s and early 1970s. And they are black holes that may form in the early universe from large overdensities. And I'll say a little bit more about how in a moment. And because they form very early on, that means they're non-baryonic, which is one of the key criteria for a good dark matter candidate. Famously, primordial black holes evaporate by emitting Hawking radiation. However, their lifetime is longer than the age of the universe if their initial mass is greater than about 10 to the 15 grams, which for context is roughly the mass of a mountain. So primordial black holes more massive than 10 to the 15 grams are practically stable, which again is one of the requirements to be a dark matter candidate. Primordial black holes are very different from other popular dark matter candidates, for instance, WIMPs, axions, and sterile neutrinos, in that they're not a new particle. However, as we'll see in a moment, their formation does typically require beyond the standard model particle physics, for instance, inflation. It was already realised back in the 1970s that primordial black holes are a cold dark matter candidate. And there was a first wave of interest in this possibility in the late 1990s. I'll talk about microlensing in a bit more detail later on. However, at that time, the Macho collaboration had an excess of events in their data that were consistent with roughly solar mass compact objects. Now, those compact objects couldn't have been baryonic because there simply wouldn't be enough baryons in the universe. So this led to sort of the suggestion that actually what they could be seeing was primordial black holes. With time, that observation went away in the sense that follow-up surveys didn't see an excess of events, and so sort of the interest in primordial black holes died down again. However, at around that time, there was a paper by Nakamura et al., and they pointed out that if you have a significant abundance of primordial black holes, then primordial black hole binaries will form at early times. And if those binaries survive to the present day, then gravitational waves from their coalescence will be detectable by LIGO. That paper, I think, was sort of largely forgotten by many people, myself included. However, as we now know, in 2016, LIGO Virgo announced the discovery of gravitational waves from mergers of massive tens of solar mass black holes. And the number of events was perhaps larger than might have been expected from astrophysical black holes. And so that led to a couple of papers which came out soon after the announcement suggesting that could at least some of those black holes be not astrophysical black holes, but primordial black holes, which could also then be a significant component of the dark matter. And this has led to a rapid rise in the number of papers published on primordial black holes. This figure shows the result of an INSPIRE search for primordial black hole. You see a brief increase in interest in the late 90s due to the Macho observations. And then 2016, there's this sharp rise to the point we're now sort of seeing nearly 400 papers a year being published on primordial black holes. A brief aside here about my personal history with primordial black holes, which might be interesting in particular to early career researchers, as an illustration of quite how random a research career trajectory can be. So I did my PhD back in the 1990s, and the main focus was early universe cosmology, and in particular probing models of inflation. And one of the things I worked on was constraining the primordial power spectrum and hence models of inflation using abundance constraints on primordial black holes. Shortly after that, in my first postdoc, I then worked on the idea that the events that the Macho collaboration was seeing were primordial black holes. And then after that, I moved on to working on WIMPs for about 15 years. However, with the announcement of the LIGO-Virgo events, that's lured me back to working on primordial black holes again, initially sort of coming back to the work I did in sort of about 2000 and then moving on to other things. So essentially my research trajectory has gone around in a big circle. So the formation of primordial black holes, there are various mechanisms, but the one that's studied most often and is probably the most minimal is the collapse of large density perturbations during radiation domination. These are the same density perturbations from which structures, i.e. galaxies, form, but on much shorter length scales and with much larger amplitude. And what happens here is if a region is sufficiently overdense, then shortly after it enters the horizon, i.e. becomes comparable with the size of the observable universe, then gravity will overcome pressure and it will collapse to form a black hole. Although there are sort of many other mechanisms, and I've highlighted just a few on this slide. The essential analysis of the requirements for PBH formation were worked out by Bernard Carr, and these calculations hold up really well. You know, they were done in the 1970s, but they really sort of capture the physics quite accurately. However, if you want to do concrete calculations yourself, then you sort of need to use some of the refinements that I'll mention briefly. So the threshold for primordial black hole formation is most simply specified in terms of the density contrast delta, i.e. the size of an overdensity at horizon crossing. And a primordial black hole will form if delta is bigger than some critical value, which is of order the equation of state parameter W, which formation during radiation domination is of order 1/3. And if that criterion is satisfied, then you get a primordial black hole formed with mass roughly equal to the horizon mass. And I've written the horizon mass here in terms of time. The lightest black holes that won't have evaporated by the present day, the 10 to the 15 gram ones, they would have formed only 10 to the minus 23 seconds after the Big Bang, whereas solar mass ones would have formed around 10 to the minus 6 seconds, which is roughly the time of the QCD phase transition, which is interesting for reasons I'll come back to later on. What I will briefly just mention, though, is that in reality, things are a bit more complicated than this. The threshold depends on the shape of the perturbation, and it turns out that the criterion is best formulated in terms of something called the compaction function. So if you want to actually do concrete calculations yourself, then I highly recommend looking into these references here. So next we can calculate the abundance of primordial black holes formed. This is usually done in terms of something called the initial PBH mass fraction, which is written as beta. And it's just the fraction of the universe which is in regions dense enough to form primordial black holes. So you take the probability distribution of the density contrast on a scale specified by the horizon mass and integrate it from the threshold value up to infinity. If you assume that probability distribution is Gaussian, and I'll come back to that assumption later on, then what you get is this expression here in terms of a complementary error function, where the sigma is something called the mass variance, and it's effectively the typical size of the perturbations on a given scale. This diagram sort of illustrates things visually. So here we've got our probability distribution in blue, sigma, the mass variance is the width, and then the primordial black holes form from rare, large fluctuations in the tail of the distribution. As we'll see in a moment, though, beta, the initial mass fraction, has to be very small. And what that means is that sigma has to be much less than the threshold value. So, the distribution is really narrow and we're really only out in the very rare tail. And in this case, our complementary error function can be approximated by this function here, an exponential. So what you see, there's an exponential sensitivity to the typical size of the density perturbations. We now want to connect the initial primordial black hole abundance to their abundance today. And the key thing here is that since primordial black holes are matter, during radiation domination, the fraction of the total energy density in primordial black holes grows with time. The primordial black hole density dilutes as a to the -3, where a is the scale factor, whereas the radiation density is proportional to a to -4, so the ratio grows proportional to the scale factor. And here we again have a visual illustration, and we see that relatively speaking, the primordial black holes make up an increasingly large fraction of the energy density during radiation domination, and then a constant fraction during matter domination. And what we can do is we can go back from today to the time they form and find roughly this relationship between the initial mass fraction beta and the fraction of the dark matter today in the form of primordial black holes. That's F. And this is roughly what we get. So if all of the dark matter today is in solar mass primordial black holes, i.e. F equals 1, then beta has to be of order 10 to the -9. And lighter black holes would form earlier on, so their initial abundance has to be even smaller. So the initial abundance has to be small, but not exactly zero, obviously. So now let's have a look at how many primordial black holes we might actually form. On cosmic microwave background scales, the amplitude of the primordial perturbations has been measured really very accurately, and it's roughly sigma, the mass variance of 10 to the -5. And what we can see already is that if that amplitude is close to scale invariant, i.e. the same across all scales, then the number of primordial black holes formed will be completely negligible. So if we take our expression for beta, complementary error function, the threshold delta C, which is of order unity, and then we've got sigma is order 10 to the -5. So you get e to the -10 to the 10, which is practically 0. We can, of course, flip that argument and work out how big sigma has to be in order to get an interesting number of primordial black holes. And here by interesting, I mean a non-negligible fraction of the dark matter today. And in that case, we need the primordial perturbations on smaller scales to be significantly larger than they are on cosmological scales. The square of the mass variance has to be of order 0.01. So this plot shows the primordial power spectrum of the curvature perturbation, and it's roughly equal to the square of the mass variance modulo factors of order unity. And it's plotted here on the bottom x-axis as a function of the co-moving wave number k in inverse megaparsecs, and on the top x-axis as the horizon mass, which is roughly equal to the PBH mass in solar masses. And on cosmological scales, this is very accurately measured. There's a sort of tiny gap between the excluded red regions, which is the amplitude measured by Planck. There are also somewhat weaker constraints on smaller physical scales, i.e. larger K values from the Lyman alpha forest. And then this line is very roughly what you require to get all of the dark matter being primordial black holes. There are some other constraints on the amplitude of the density perturbations on small scales. For instance, large density perturbations would distort the CMB, and then large density perturbations at second order lead to large tensor perturbations, and that would show up as gravitational waves, so-called scalar-induced gravitational waves. And these shaded regions are the regions that are excluded by current experiments. And then the dashed lines are what we could expect from the sensitivity of future experiments. So at the moment, potentially pulsar timing arrays rule out this region here, but in the future, there's really the potential to push these constraints much further down. There are a few important deviations from the simple scenario I've talked about that I'd like to mention. The first of these is a phenomenon called critical collapse. It occurs in general in gravitational collapse, and Nima and Jadamzik pointed out that it would apply to primordial black hole formation. And as a consequence, the mass of a black hole depends on the size of the fluctuation it forms from, as this power law here. So it's typically still of order the horizon mass, but it grows as a power law of how big the actual fluctuation is relative to the threshold value. And the reason why this is important is that even if all of the primordial black holes form at the same time, they won't have exactly the same mass. There'll be some spread in masses around the horizon mass. Another thing to mention is the effect of phase transitions. At a phase transition, pressure is reduced. That then reduces the threshold for forming a primordial black hole and hence increases the abundance of primordial black holes formed on the corresponding horizon mass. And this is a plot of the fraction of dark matter in the form of primordial black holes for a large power spectrum, which is not quite scale invariant. And in particular, we see around the QCD phase transition, you get an enhancement of sort of roughly solar mass primordial black holes. So again, if you want to accurately calculate the mass function of primordial black holes, this is an effect you need to take into account. Another very important thing is non-Gaussianity. In the simple illustrative calculation, I assumed that the probability distribution was Gaussian. And it was pointed out back in the 1990s that since the primordial black holes are forming from rare large density fluctuations in the tail of the probability distribution, even a relatively small amount of non-Gaussianity will significantly affect their abundance. More recently, it's been realized that because of the nonlinear relationship between density perturbations and curvature perturbations, even if the curvature perturbations are Gaussian, then the density perturbations, which is what matters for primordial black hole formation, will inevitably be non-Gaussian if they're large. And so, what that's telling you is that actually the Gaussianity assumption isn't a good one. We'll look briefly now at inflation models that produce large density perturbations. What do you need to do? Well, in the simplest slow roll approximation, we get this expression for the mass variance, the typical size of the perturbations, potential v to the 3/2 divided by the slope of the potential v prime. And so what we're seeing is that to get large sigma, we need small v prime. And again, it was pointed out in the 1990s that you can sort of do this by inserting a plateau in the potential. However, it is important to note that in the ultra slow roll limit, i.e. as v prime tends towards 0, this expression isn't accurate. You have to do numerical calculations. And also ultra slow roll affects the probability distribution of the fluctuation. So it's another reason why they're unlikely to be Gaussian. There are a few requirements for a successful PBH producing inflation model. The first thing is you have to match the observations we already have on cosmological scales of not just the amplitude of the perturbations, but also their scale dependence. As we saw a few slides ago, you then need to have the amplitude of the perturbations being several orders of magnitude larger on smaller scales, and then eventually inflation has to end to have a successful hot Big Bang. It turns out that in single field models, it's really quite hard to satisfy all three of those requirements. And typically you need to fine tune your potential. And so here we've got an illustration on the left of a potential which would work. This green shaded region corresponds to the region of the potential where perturbations on cosmological scales would be produced. And then here in this box, we have a tiny feature inserted into the potential, which we can sort of see the zoom into. And what happens is the bump slows the field down, which is what we need to produce the large PBH forming perturbations. But then eventually it gets over the hump, the potential steepens and inflation ends. And here on the right, we've got the corresponding primordial power spectrum, simple calculation in blue, more accurate numerical one in red. So here we're matching the amplitude and scale dependence on cosmological scales and then getting the large enhancement required to form primordial black holes. And typically this rise is roughly k to the power of 4. So you can do it in single field models, but you need fine tuning. So a way to avoid that is sort of decoupling the three different requirements. And typically you can do that by having multiple fields. And one potential way of doing that that's very popular is hybrid inflation with what's called a mild waterfall transition. So in hybrid inflation, we have two fields with a potential that looks like this one here on the left. Initially, the field slow rolls along this single valley here, but then we get to a point, there's a transition to having two global minima, and the field sort of rolls down into one of them. And if this transition happens not too fast, but not too small, the field gets kicked around by quantum fluctuations, and you get this large, broad peak in the primordial power spectrum. As you may know, overall, there are many hundreds of inflation models, and there is some subset of them that can produce large PBH-forming perturbations. Here is a brief list, and if you're interested in learning more, then I'd recommend those review papers. So we've seen that, in principle at least, primordial black holes can form in the early universe. What dark matter is, it's at the end of the day, it's an observational and experimental question. So let's now have a look at the observational constraints on the abundance of primordial black holes. As I mentioned previously, we don't expect them all to have the same mass. Initially, the constraints I'm going to show you are making that simplifying assumption, but later on, I'll talk about the effects of looking at more realistic extended mass functions. So some of the sort of most powerful and cleanest constraints on primordial black holes and compact objects in general come from gravitational microlensing. And microlensing is where the separation of images is of order a microarc second. So this is too small to resolve, but instead you get a temporary brightening of the object. And in particular, stellar microlensing is when a compact object passes between the line of sight between the observer and the star is temporarily brightened. And various collaborations, including Macho, Eros, and Ogle, have been monitoring many millions of stars in the large and small Magellanic Clouds for many decades now. And then there's also more recently been a survey of M31. And if all of the dark matter was made of compact objects, they would have expected by now to have seen sort of hundreds, if not thousands of events, but in fact, they only see a handful, roughly consistent with what you'd expect from stars. So we end up with this exclusion plot on the fraction of dark matter in the form of compact objects. The bottom x-axis is mass in terms of solar masses, the top one, mass in terms of grams. And all of the plots that I'm going to show you like this are made using Bradley Kavanagh's PBH bounds code. And so what we see here is we've got constraints down to the percent level across a wide range of masses, from planetary masses through to many times the size of the sun. And the latest constraints from Ogle, they go up to sort of about 1,000 solar masses. There are also other microlensing constraints, for instance, from the magnification distribution of supernovae. Icarus would unfortunately take too long to explain in great detail, but it is one of a number of what's called supermassive stars. Stars at a redshift of order of few that are temporarily magnified so that they're individually visible. And in that case, it turns out that this can actually only happen if the majority of the dark matter is smooth. The magnification is reduced if the dark matter is largely in compact objects. There's also a constraint from quasars. In this case, you have multiple lenses formed, and then individual lenses could then be microlensed, and that's not something that appears to be seen at a rate above what's expected from stars. So we get these sort of additional constraints which also populate the planetary and stellar mass region of parameter space. It turns out that the gravitational wave events that started the excitement in 2016 actually place a constraint on the abundance of primordial black hole dark matter. So as I mentioned before, Nakamura et al. Showed that if a significant fraction of the dark matter is in the form of primordial black holes, then you will get primordial black holes binaries forming. And this is just if they happen to be close enough, a third one comes along, there's an exchange of angular momentum, and they can form a binary. If the orbits of the binaries aren't perturbed significantly as structure forms, then it turns out that a significant fraction of those binaries would be merging today. And in fact, the merger rate would be substantially larger than that measured by LIGO. So provided our understanding of the formation and survival of primordial black hole binaries is correct, then again, we get these sort of 10% to percent level constraints on the abundance of primordial black holes from roughly a solar mass up to sort of hundreds of solar masses. There are also constraints on massive primordial black holes from what are called dynamical effects, as in how there's a gravitational interactions would affect the properties of stars. In small dwarf galaxies, the stars are dynamically heated and their distribution would be puffed up. That's not something that's observed. And also, massive compact objects would affect the orbits of wide binary stars. Stars that are gravitationally bound together, but they're a long way apart, so they're weakly bound. And the cumulative effects of lots of interactions with passing primordial black holes would end up breaking up those wide binaries. And so these constraints, they sort of kick in and are really quite sort of powerful when we get to very big, very massive compact objects, or typically 1,000 solar masses and above. There are also constraints in this mass range from the consequences of accretion of gas onto primordial black holes. There would then be radiation emitted, and that can have two different classes of effects. Firstly, in the past, it would modify the recombination history of the universe, and that's something that can be constrained, for instance, from CMB anisotropies. And then also, it would be happening, accretion onto black holes today in high density regions, and would lead to sort of emission, which would be visible as, for instance, X-ray and radio sources in the Milky Way, or you could heat the gas in dwarf galaxies. And again, all of these things are really putting very tight constraints on the abundance of primordial black holes more massive than about 100 solar masses. We need some ideas, though, for how to probe lighter subplanetary mass primordial black holes. And a lot of the ideas for doing this are around their interactions with stars. And there are a few general possibilities. So when a primordial black hole passes through a star, it can capture the primordial black hole, and then the star will get accreted onto the black hole and destroyed. Alternatively, if you're going through a white dwarf, you could heat it up and make it explode. What, as far as I'm aware, is the state of the art here is this paper by Montero Camacho et al. From a few years ago. And they say that currently there are no constraints. There could be constraints in future, but you'd have to work out the signatures of stars being destroyed, And if you were wanting to use the survival of neutron stars, you need an environment where you have a high dark matter density and a low velocity dispersion. And that could be a globular cluster, but only if it has a dark matter halo. And my understanding is that in general, astronomers don't think that globular clusters have dark matter halos. They're star clusters. There are also some ideas as to how primordial black hole capture could disrupt the formation of stars. And that's something that needs to be developed to be turned into a concrete, reliable constraint. I mentioned at the beginning that primordial black holes less massive than 10 to 15 grams will have evaporated by the present day. Slightly more massive ones will have started evaporating and will be kicking out lots of, for instance, high energy gamma rays. And so we can constrain their abundance by looking for the products of the evaporation. And here what we see is, again, we have really tight constraints down to about 10 to the 16 grams. But then once we get to sort of just a bit below 10 to the 18 grams, the evaporation hasn't really started. So this doesn't work anymore. Here is a compilation of the tightest of the constraints I've been telling you about. So these, again, I'm just to emphasize, they assume a delta function mass function, i.e. that all the primordial black holes have the same mass. And of course, any constraint involves modeling assumptions. And so here there are various standard assumptions about the distribution of primordial black holes that are made. So taking these at face value, what we see is these solar and multi-solar mass primordial black holes that there was great interest in after LIGO Virgo, they're constrained by various methods, microlensing, the gravitational waves, accretion constraints, and dynamical constraints. So it appears that multi-solar mass primordial black holes making up all of the dark matter is excluded. There is this window, though, in between the evaporation constraints and the microlensing constraints, which corresponds to roughly asteroid mass objects, where they could make up all of the dark matter. And that is intrinsically because these things are very hard to probe. We haven't managed to do it yet. A couple of things I'd like to expand on. So, as I told you earlier on, we don't expect a delta function mass function. We expect the black holes to have some spread in masses. And what that typically means is that the constraints on the fraction of primordial black holes are smeared out. So these plots I'm showing you are from a paper by Bernard Carr and collaborators. It's a few years old, so the constraints have changed since then, but I'm showing it to you because it's a nice illustration of what happens. On the left, we have the constraints for a delta function or monochromatic mass function. And then on the right, we have those for a log normal mass function of a particular width. And it turns out a log normal is a reasonable but not great fit to the mass functions produced by particular inflation models, which produce an interesting number of primordial black holes. And so what you see is, if we focus on this HAC microlensing constraint, the tightest value is a bit weaker, but it applies across a wider range of masses. So what we're seeing is the gap between the evaporation constraints and the microlensing constraints becomes narrower once we're considering more realistic mass functions. I should also mention that there are things that have been observed that could potentially be explained in terms of primordial black holes. And if this is something you're interested in, then I would recommend this review paper. I won't talk through all the possibilities, but for instance, there are small numbers of microlensing events, which could be due to primordial black holes. And here we've got a subset of supernovae that are calcium rich, which it's been suggested could be due to primordial black holes causing white dwarfs to explode. So there are things which could be due to primordial black holes, but then you've also got to sort of make sure that everything matches up with the constraints, that the observations which tell us that primordial black holes of a given mass, we don't think they're there. I focused on primordial black holes which haven't evaporated by the present day, because my main interest is in dark matter. But nonetheless, lighter primordial black holes are still interesting. As we've already seen, they're a way of constraining the physics of the early universe, and in particular constraining the amplitude of the density perturbations on scales that are much smaller than those probed by cosmological observations. And what I'm showing you here are evaporation constraints, which include both the primordial black holes, which are still evaporating today, plus those that would have evaporated at earlier times, and in particular, primordial black holes that evaporate around the time of nucleosynthesis would mess up the very successful predictions of nucleosynthesis. One thing to mention here, though, is this assumes that primordial black hole evaporation just completes, that it doesn't suddenly stop. There is some sort of a lot of interest in the possibility of what's called the memory burden effect. I'm not an expert on this at all, but apparently this is when you get the emission back reacting on the black hole and essentially sort of stopping the evaporation. So finally, to wrap up, I'm going to talk very briefly about what I think are some of the key open questions in the field. An obvious one is how to probe these tricky to probe asteroid mass primordial black holes. There are some ideas here, for instance, the femtolensing of gamma ray bursts, and that's sort of gravitational lensing where the separation of the images is a femto arcsecond, clearly far too small to measure, but you get interference fringes in the emission. Another idea is looking at gamma ray bursts using two different satellites, and such that one would be picolensed and the other wouldn't. And then X-ray pulsars, microlensing could be used in that case because the wavelength of the light is far shorter. And a thing I possibly should have mentioned before, but I'll mention it now, is a key limitation of stellar microlensing is that using optical wavelengths, you actually get to the point at about 10 to the 22 grams, where the wavelength of the light is comparable to the Schwarzschild radius of the black hole. And what that means is that wave optics effects become important, and that reduces the magnification, and therefore you don't get observable microlensing events anymore. And so by being a little bit cleverer with your observations, for instance, using a survey of white dwarfs in the LMC, you can get constraints which are tighter, but you can't push down below 10 to the 22 grams. And hence we need sort of different ideas using shorter wavelengths of light to try and probe this gap in between the microlensing and evaporation constraints. And then finally, clustering. This is something that's potentially extremely important. In particular, it would affect the merger rate of PBH binaries and potentially some of the other constraints too. Now, it's been known for quite some time that if primordial black holes make up a large fraction of the dark matter, then you will get clusters of primordial black holes forming shortly after matter radiation equality. And this is much earlier than when you typically get dark matter halos forming. And the reason for this is that because the black holes are discrete objects, there will be Poisson fluctuations in their abundance, and hence you get this early structure formation. This is something that's been simulated up to a redshift of about 100, but you can't run these simulations through to the present day and study how the PBH clusters evolve within larger dark matter halos. And in particular, it's hard to study how the primordial black hole binaries will be affected by the clusters forming and then subsequent structure formation. So this is, I think, for me, one of the sort of big interesting but hard problems in the field. Another thing I'd like to mention just very briefly is there's some interesting physics if primordial black holes make up a fraction of the dark matter. And in this case, they would accrete halos of particle dark matter. And in fact, if you had a mixture of primordial black holes and WIMPs, you get large amounts of WIMP annihilation, and we would have already seen the gamma rays. So practically, dark matter being a combination of WIMPs and primordial black holes has already been excluded. So to wrap up, Primordial black holes can form in the early universe, for instance, from the collapse of large density perturbations. However, to produce an interesting number of primordial black holes via that mechanism, the amplitude of the perturbations must be about 3 orders of magnitude larger on small scales than the measured value on cosmological scales. You can do this in models of inflation, for instance, with a feature in the potential or with multiple fields. However, it's not natural or generic. Most inflation models for most parameter values don't form an interesting abundance of primordial black holes. We've also talked about constraints on the abundance of primordial black holes from observations. That's the most important thing at the end of the day. And there are various constraints from gravitational lensing, from their evaporation, dynamical effects, accretion, and other astrophysical processes. The current situation is it appears, unless we're really getting something really quite badly wrong in our calculation of the constraints, that solar mass primordial black holes probably can't make up all of the dark matter, but lighter asteroid mass ones between about 10 to the 17 and 10 to the 22 grams could. But as we noted, the limits on the abundance are collectively tighter for realistic extended mass functions than for the simple delta function that's often assumed. And then finally, we talked very briefly about some of the key open questions in the field, how to probe light primordial black holes, and also the clustering of primordial black holes. So that's it. Thank you.